Okay, so this is Terry from National Tsinghua University, and today I'm going to talk about our recent project, Search for Planet 9 with IRAS and Akari data. And first of all, I would like to appreciate the contribution of our co-author listed here from NTHU, NTHU, JAXA, and ANU. So to understand our motivation on this project, let's go back to more than a decade ago when astronomers tried to analyze the orbit of distant capable objects, including Sedna and other Sedna-like objects. They noticed that these objects show peculiar orbital clustering not only in argument of perihelion but also in the physical space. This is very weird. So imagine this situation: people are walking at Taipei main station on the same way and looking at the same direction. So this thing cannot happen unless there's someone or something forced them to do that. And we apply the same logic here. This orbital clustering cannot happen randomly due to chance unless it's related to an aerodynamical mechanism. So simulation work done by Konstantin Patigan and Mike Brown in 2016 suggests that the probability for this orbital clustering happen randomly is only 0.007%, which is almost impossible. And they also suggest that a giant distant planet, so-called Planet 9, with at least 10 Earth masses and a semi-major of 700 AU, can maintain this orbital clustering. Actually, this is the video of the simulation, but due to the technical problem, I just explained here. So those blue orbit here are that represent for the distant capable object, while the pink one is the possible orbit of Planet 9. And at the beginning of the simulation, you can see those blue orbit will distribute everywhere in the space. But after longer time evolution, for example 1 or 2 giga-years, those blue orbit were scattered to the opposite side compared to the orbit of Planet 9, similar to this figure. And this is consistent with what we observe for the orbital clustering these days. And that's how they come up with the Planet 9 hypothesis. And if true, it will improve our understanding about the dynamical structure and the history of the our solar system. So indeed, since the discovery of Neptune and the demotion of Pluto, our solar system still remaining with 8 planets. And simulation already predicted the existence of Planet 9, so our most important task is to identify Planet 9 by observation. Actually, in the past, there are a lot of crews try to search for Planet 9 in optical, but it turns out that they only constrain the orbital parameter for Planet 9, but without proposing any specific candidate. So what happened here? Because Planet 9 was predicted to have a magnitude of about 26 or even fainter, and sunlight needs to travel twice from the sun to the planet and then reflect back to the Earth. It will degenerate faster than the thermal emission from Planet 9 itself as a function of distance. So the thermal emission here only needs to travel once. So in this case, the infrared survey are way better than optical survey for Planet 9 search. And another problem is, we don't know where exactly Planet 9 is on its orbit, so that's why we need the all-sky survey. And there are 2 far-infrared all-sky surveys which are IRAS and Akari can meet those requirements. And there are 2 recent far-infrared search. The first one, they only use IRAS data, and the second one, they use the combination of IRAS and Akari. But the Akari data they use is the Akari bright source catalog. In this catalog, moving sources are excluded by the stacking process, and this is not good for Planet 9 search. Instead, we use another dedicated source list for Planet 9 search with the Akari monthly unconfirmed source list. In this dataset, moving sources are included, and those moving sources can only detect it in several hours, but not after several months. So this is very good for Planet 9 search, and we thank to Dr. Jimamura and Nagarawa from JAXA for giving us the access to Akari and USL data. So our idea is, because the epoch difference between IRAS and Akari are 23 years, which is large enough to detect a slow motion of Planet 9. And to search for Planet 9, we expect that it should be detected in IRAS in 1983, and after 23 years, it will move to another Akari position. So, at the beginning of our selection process, we need to estimate the expected flux and expected orbital motion for Planet 9. And in this work, we search for sub-Neptune planet within 500 to 700 AU. And at the upper limit of the mass range, you can see that the expected flux approaches the detection limit at 700 AU. And similarly, the orbital motion also decrease exponentially if you go further and further on the x-axis. To narrow down the total number of IRAS and Akari, which is about 2.4 million sources, we first remove the stationary and too bright sources because they are too unrealistic to be a moving object like planet. And the second one, we exclude a source near the galactic plane and galactic bulge because these two regions will significantly affect to the flux measurement. And then we make a list of single IRAS and Akari detection. After we have a list of moving objects, we need to make sure that they are all above the detection limit of IRAS and Akari. Then we try to find all the possible candidate pairs. To do that, for each IRAS source, we try to find all possible Akari components within 42 to 70 arc minutes corresponding to 500 to 700 AU. And at this step, there are 13 IRAS and Akari pairs in total before the visual image inspection. So after the visual image inspection, there only one candidate survived. And this candidate was first detected in IRAS image in 1983. And after 23 years, it disappeared from the same location in Akari image. And we expect that it will move to Akari position. As a small panel here, it is the Akari detection probability map. We also check the Akari flux map. So the left panel here, at the epoch in December 2006, there's one detection here, and the flux at 90 micron in the catalog is 0.27 Jansky, which is still above the detection limit. But 6 months before, there are no detection. This is consistent with our expectation that Planet 9 should disappear from the same location after 6 months or in the 6 months before due to the parallax motion. And we also reported this candidate in our recent paper published in CASA in May 2025. And luckily, this paper got an attention score of more than 1,000, which is very high as my first paper in astronomy. And it was also featured in many news media, including Science Magazine, Astronomy Magazine, and many YouTube videos. I think this is very good to promote our work to astronomers and non-astronomers. So, what's next after this paper? Because IRAS and Akari detection alone cannot determine the full orbit of our candidate. So we need follow-up observation, for example, Subaru HSC and dark energy camera with larger field of view to identify the Keplerian motion of our candidate. So in conclusion, simulation already predicted the existence of Planet 9. And in this work, we use the combination of Akari moving sources and IRAS sources to propose one promising candidate within 500 to 700 AU, and if Planet 9 can be confirmed in the near future, it will become one of the highest impact discovery of this century, because a new solar system planet can be identified by modern astronomers, and we appreciate audience to stay tuned for our next update. So that's all for my talk. Thank you.
Questions for the speaker?
So you showed a map in which the planet 9 was moved to a new position in revised catalog. So yeah, in this one. So my question is, what is the significance of detected source? Means how much sigma detection is there for the detected source? Because in maps normally there are a lot of artifacts as well. And there is only one map, I think, in which you have detected it.
Because the requirement to determine the detection in Akari and USL is only two detection. So no matter how many scans pass by the object, so with only two detection, so it's quite difficult to have an error bar and to estimate the significance.
Not error bar means you can measure the noise in empty space and measure the flux on the source and divide by the signal to noise ratio basically of the source.
Yeah, but you know, here is in the Akari image, is only the original purpose is only for the Akari bright source catalog. But the catalog we use is for the moving object. So actually, here you cannot see the real detection at Akari position, but instead we need to rely on the Akari detection probability map to see the detection at each scan. Yes.
No, I'm just asking signal to noise ratio of what you have detected. It's okay, we can talk later. Yeah, thank you.
It's very weird. I complain a lot, but their team doesn't release this flux map. So they do something special. I mean, they detect from a detection map, which cannot be used to measure signal to noise ratio. So
Maybe we should take out a question.
Just on the following slide, so I didn't quite understand on the next slide. I didn't quite understand. So you have occurring observations 6 months apart. So why don't you see the object on both dates?
Because after 6 months, then due to the Earth orbital motion around the sun, and you cannot see object at the same location on the sky.
But so you should somehow know that it's not too far away. Can't you search?
Yeah, it's not too far away, but the Akari will classify them as a different source.
Okay.
Yes.
So you didn't look for it.
Yeah. So in this work, we only look for the pair, one Iras and one Akari. But in our second project, we are trying to look for the triplet detection, including one Iras and two Akari. So the difference between two Akari is 6 months. We try to find a possible triplet.
And another question is, can you comment on this discovery of ammonite, which is not clustered with others that not like objects?
Compare with
There is a newly discovered Sedna-like object, which has an opposite center.
Yeah, actually, okay, I'm sorry. Actually, I have estimation. Compare the orbit of our planet 9 candidate with the other Sedna and Sedna-like object. So I think one of these two should be harmonized, but I forgot the name. Yeah. Yes.
No, I don't. Well, anyway, so they don't have. They are not the new one is not clustered with the other object, so it kind of is a proof that this clustering is caused by the planet 9.
Yeah, but only one of them cannot directly rule out the planet 9 hypothesis.
Okay.
Yeah.
Okay, thank you.
Other questions? If you have a question, yeah.
How did you derive the mass and distance of your proposed can?
Oh, okay, that's a good question because due to the time limit, I cannot show that here. Because we already know the angular separation between IRAS and Akari source. Then based on the expected orbital motion, we can easily derive the distance, which is 645 AU. And then when we have the distance, we can and also combine with the flux, then we can derive the mass, which is 11 mass. Yeah.
So we have to move on to the next talk. Let's thank the speaker.